my name is Rene Pronovo. I'm the Director of Services at Maya. I'm definitely a project guy. I like doing projects. I like all those sexy slides, but I like just to do fun projects, and that's basically what I've been doing my whole life. 15 years in the PLM, I've done automation of crash test simulation, aircraft interior design, certification, compliance, nuclear power plant refactoring, how to simulate ins and outs of equipments, stuff like that, connecting data centers, a lot of IoT projects, digital twins of data centers. So I like the challenges and pains that comes with all these projects. I like that in my professional life, as well as outside of that, I like to do a lot of triathlons, Spartan races, stuff like that. So I'm definitely always up for a challenge, either personally or with my team. I've got a great team. Some people here in the UK, thanks for joining today. It's about half of the organization. We mentioned about 200 people earlier. About half of that are dedicated to doing customer projects. So we have about 5 teams, just so you know, dedicated to PLM type activities, dedicated to simulation. We have 2 custom development teams, either dedicated to Siemens portfolio or web, IoT, other real-time engine monitoring customizations, as well as an AI. I have a data science group that does AI projects. I'll just give you an idea. So I kind of like projects where we can cross-pollinate, do things together. Where can we get creative? Thanks, Nick, for setting the stage about the digital twin and simulation. I'll just talk about one more ingredient, and that's the automation aspect. It doesn't always fit in, but there's always a case where it makes sense for a company to look into automating some of their workflows. Here's one of those slides where we're talking about the impact over the next years, and it says, knowledge automation is one of the major disruptors, and yes, it can have an impact of 9 trillion. There's 2 ways of looking at that. I think from a technology point of view, I could say yes, there's a lot of technology that's ripe for that, for embedding IP, for automating things, which is one way of considering it a threat. The other aspect of looking at it, and this is more where I'm talking with my customers, is that they come see me and say, I don't have the skill set to do this type of simulation. I don't have the people, or my workforce is volatile. So if I can capture more of that and embed it into my tools, I'm really creating a more reliable process, more sustainable process, and that when my teams that are moving around, they can incrementally improve that. That's something more sustainable for my engineering team. So that's kind of more the dynamic of why capturing knowledge and why automating knowledge that I see that's beneficial. Related to that is the competitive aspect to it. So I like putting this pyramid in the sense that I think a lot of people have PLM tools, Teamcenter, or different things in CAD simulation. And all these tools are great, and they're kind of designed generically to cover many different industries. Some of them, there's modules that are very point specific for hydraulics, composites, et cetera. But it's only when you start embedding your own company's specific IP or your own workflows that you really start leveraging those tools and that you can become more competitive. And that's kind of there's traditional drivers around quality, cycle time, efficiency. But what I'm hearing more is, how can I make this digital twin accessible to the sales team? How can we leverage that so that they can take some benefit from it? And those are some of the examples that I'll give today where we've kind of created automation tools that are actually driven by the sales team, which is kind of interesting. So, and again, just enabling the value chain, so embedding more expert knowledge and stuff. So I'll jump out of this and I'll jump right away into, one more slide. The opportunity landscape is quite large. What I mean by that is that sometimes we'll talk about automating a simulation process or a manufacturing process or a smart CAD model. These are all point things, and sometimes they're very valuable individually, and sometimes we're looking at more the end-to-end process. And I like to think that's why I have customer at both ends, because a lot of the times customers are driving the requirements or what they want, and they're the ones who get the product at the end. So the better I can kind of accelerate or connect those through workflows, I find the more logic they are, the more people in the organization are involved, and the more robust they come actually for companies. So I'll jump in quickly to a bunch of examples now. So I think you mentioned it before, the Canadian digital twin, I guess. Are there any hockey fans here by any chance? One, yes, thank you. And so
is that ice hockey or is that
ice hockey? So we've had the chance to do a lot of cool stuff in hockey, and so if you'd ask a Canadian company if they can help Canadians get better at winning in hockey, we would definitely take that challenge. So I don't know, maybe in the UK is it golf or tennis or something else? I don't know if it's rugby, what we can do. So as you can see, there's definitely a lot of equipment involved in hockey. And so to make that equipment better is a nice challenge that's fun to do. I don't know if we can do anything about this guy's teeth here at the bottom left and look at the durability of that, but that's also one of the fun parts of hockey.
We have a number of healthcare projects, so yes.
Yeah, we do healthcare projects as well. So it's definitely a great sport, but a fast sport, a contact sport. To give you an idea, the slap shot here that he's doing with his stick goes about 106 miles an hour. So the stresses put on that stick and then the mask that receives it of the goalie in the face are actually a lot of challenges in designing that so that it's durable, but also flexible, lightweight, good for the athletes to perform. So first project I'll talk about is the automation of hockey stick design space exploration that we did. The first thing that we had to do was actually just come up with the right CAD model. So how do we take that stick, put it into flexion so that the hockey player can do it? As you can see, I'll just back up. The amount of curve that goes into this stick is quite significant. They're often in aluminum or sometimes in composites. This one's actually in aluminum, the example. What we did is come up with the right CAD model. From there, we came up with the right finite element model. And from there, we wanted to put together kind of a design exploration. So we have a multidisciplinary optimization tool to look at the durability of this. So it's all about reducing weight, increasing flexibility, but also passing the fatigue cycle that you want, the amount of slap shot hits that you can do in a game and make sure it doesn't fail. And you'd be surprised, actually, they fail a lot in games. You'll see sticks break every game. And it's actually quite dangerous because the sticks fly into the other players' faces. So it's always kind of like on an edge of how, to the limit we can do these designs. And you'd actually be surprised the players work very closely with stick designers to actually come up with these designs because they're very particular on how they hold their stick. So the challenge from that was we came up, there was 14 different variables for different thicknesses, shaft, layer, materials, example, curvature, coming up with about 300 different designs. And what we wanted to do is automate the design space exploration of that. So the key challenge in that actually is mostly around generating an automated, updated CAD model and an FE model. So from there, we came up with all the different variables that can update through these kind of looping cycles that we're going to do to explore the design space. And what's fun about that is that after that, from all the different design variables that we'd put together, you can figure out which variables, this is kind of like a normalized curve from for each of the variables, and we figure out which ones are passing. So you could figure out which variables should we minimize, maximize in order to get the best performance. And then look at different trade-offs. And so from there, we can look at different alternatives and figure out which the best one is. So the outcome of this project was after we had kind of set this up, we had a tool that, in this case, we had 300 different evaluations that would just crunch for about 18 hours. And from there, we had options for sticks that were 46% lighter and 65% more flexible, passing the durability requirements that were required. So this was more of a fun project for us, actually. We didn't have to convince any of our engineers to jump on this project. So related to that, once we have a stick that can shoot a puck at 106 miles per hour, you got to be able to design a helmet that can withstand that impact. So a lot of this one is a helmet that's actually in composite material. So that's one of our specialties, how to do the layup of these composite materials and actually how to do the simulation of all these layouts, as well as the curing. So when we started working with Bauer, they wanted to increase their production, actually, was one of their challenges. So while maintaining that performance capability, maintaining that impact capability. So this was about improving production cycle time. And what we did is we did a multiple of, we reused a digital twin and did mold thermal cycle optimization from there. And from there, we were able to reduce 30% the curing time related to producing these masks while maintaining quality standards. So I'll jump out of hockey now. Sorry, I don't have any more sports examples, but I'll talk about injection molding. Husky injection molding, I don't know if you guys are familiar with them in the UK. They're based out of Luxembourg, but they have a big operations in Canada and the US. We work closely with them. They produce the injection molding equipment such as you see below here to produce the type of bottles that you see here for Coca-Cola, Evian, et cetera. There's actually a lot of engineering. It's quite a complex project. Does anyone work in the injection molding industry by any chance? The amount of simulation, I believe to design a bottle, there's over 30 different types of simulations. If you can believe it, tilt, angle, droppings, pallet stacking, drop tests, filling liquids, tightness, durability. You want to minimize the plastic, minimize the weight. There is a significant amount of simulation that goes in the bottle design, as well as the mold design and cooling channels and heating channels to actually fill these. And one of the challenges of that industry is that it's an industry that moves a lot. You'll see new bottles that come out every few months. So the ability to quickly produce new molds that meet all the requirements are quite high, and that's one of the challenges that they have. So, and as you can see in one of these machines over there's maybe 100 or 200 of these cavities that are all complex sub-assemblies, as you see there, with lots of small parts that need to be manufactured and cleared with tolerances. So the ability to do that quickly is very important. This is an example of, I'll call it CAE democratization, so making simulation accessible to non-simulation experts. One of the challenges they had is when they were the mold designers, or more manufacturing people and not simulation experts, have to design the cooling channels inside a mold. This is a generic example, but what you're seeing is the automation. This is an automation wizard that allows non-simulation experts to run thermal validation on their designs. And the challenge that they had before is that the cycle time between the designer doing the molds and sending it to the simulation team was too long, and they weren't doing enough simulations, and it took a long time. So what we decided to do is to create a tool for them that enabled them to just choose their faces, choose their boundary conditions, not knowing what a mesh is or a boundary condition is, just understanding thermal loads and what the surfaces were. And from there, they were getting automatic pass or fail validation, basically, and automated reporting. And all this inside their PLM system, and it was traceable. So later on in the cycle, when they wanted to maybe put it in production, the CA expert could actually just look at the report and make sure everything was okay. So the end result was actually not only were the designers enabled to do simulation, but the amount of simulation done increased a lot, because the designer could do a design and go, oh, let's check it out. 15 minutes later, hey, it's good. I've got this instead of waiting a day. So he'd iterate much more. So the amount of simulation runs increased a lot. We had a log file of what was calling on the licenses at the time, and it was 15 times increase of simulation for them. So the performance of their product improved significantly, and as well as the manual time to do those dropped by 90%, because now everything was automated. So that was a nice project for them. The next project, also related to Husky, this is the one where it covers actually the full span, from sales all the way to manufacturing. This was a large project. We were multiple people working on this at Maya. It's called the Next Generation Operation Model. As I was saying before, one of the challenges at Husky is that the customers have a quick turnaround cycle. They want to be able to produce bottles quickly and say, hey, we want some new molds, we want a new model out in the next few weeks from now. So how can Husky provide these molds in a timely fashion? This is a process that used to take weeks. Send drawings to engineering, send the request, update the parts, design, send it to manufacturing, et cetera. What we put together is a process where the input was a web interface, where the customer manager, relationship manager, a sales guy could work directly with the customer, input configurations, and that's how the process started. The punchline is that 3-4 hours later, you actually have the manufactured part. So you went from something that took weeks now to days. And that's really a game changer for some of their customers, where they want now to have access to parts very quickly. And even before ordering the part, they can get the cost of the part. So from there, you'd have a web entry where people would put geometry in. That would call on a bunch of tools that would then build the right CAD assembly based on hundreds of design rules. So all the IP was captured in the design rules based on a whole bunch of expressions. We'd run some optimization on there to make sure we had the right parts, the right shapes. From there, that would produce the manufacturing information in 3D that would produce the inspection, automated inspection, as well as produce the G-code for the CNC machines, and then the part was manufactured. So this is a solution that's been rolled out now at 2 sites in Husky. So when customers around the world, or the sales teams working with Husky around the world, they can actually manufacture in 2 sites right now, in Luxembourg or in Canada, by calling on this system. So it's really a nice game changer. And this is incorporating a lot of different things, from automating CAD, automating optimization, automating machining, all that in a workflow that's no man in the loop at the moment. So we're currently working with them with different of their product lines to do this, because we've done it on some first product lines. How am I doing on time? All right.
About 5 minutes left, running.
Okay. Pardon?
I know you talk fast.
Yeah, I do talk fast. The next project is more about simulation data management. We worked at Orbital ADK. One of the challenges that they had, of course, if you're in the rocket business, there's a lot of simulation going on. And one of the challenges that they had was the relation from data that was produced, and manufacturing information, and what the simulation analysts were doing. So they couldn't trace the results well back to the parts, and that was causing a lot of headaches and confusion later downstream, when they were actually trying to validate some of their spacecrafts for flight. So what we ended up doing with them is creating a simulation data management strategy for them. So they had over 26 different simulation tools, a lot of different sites, over 600 analysts working, and it was a bit of a chaotic process. So by embedding that in a simulation data management process, they were able to streamline a lot of their workflows. So we captured a lot of their different workflows, created a customized data model for geometric data relating to the designers, also non-geometric data, so load cases, materials, all these things, all the libraries that are supporting all the simulation. And then that way you'd always have the full traceability of what was being done in design versus actually what was being simulated. And that actually ended up, they're still rolling it out. It's supposed to touch 600 analysts, so it's quite an extensive project, but they're expecting a much stronger collaboration and shortened cycle time and better resource utilization out of this is what they're expecting at the moment. All right. Another one related now, again, this is covering from a customer request to manufacturing, but on a little bit of a smaller scale. This is an automotive tier 1 supplier that we've worked with that has a catalog of standard parts, about 150 standard parts, but that you can also customize. So they can say, hey, can we machine this off or get this and order 5,000 of these parts. The challenge that this tier 1 supplier had was that the process for a customer to call in, hey, can I get that, would take a few days for them to get a quote, and that wasn't expedited enough for them for the customer. So what we did is kind of similar to what we did on an earlier project. They already had a custom online portal. So from there, we created a connection that from the standard library of parts, we would take the customer's input on the CAD changes and actually automatically detect all the features that were being machined. And then from there, we can optimize the CAM setup, generate the CNC code, and then we could derive a quote from that, much more reliably than what was being done manually. And so that was really shortening the process. So in the end, this is a process that would take manually 4 hours to a few days, pending who was involved and what the requests were. And this brought this down literally to 10, 15 minutes, online quote, and they get the price and they can execute the project. So this is the type of process, again, driven by the end customer now. Sales isn't even involved. They're just online and they get what they need. All right. And I believe this is my last example. This is really simulation embedded for sales again. One of our customers in industrial equipment, when they're committing to sales, so when a salesman's working with them, the objective of this equipment, what they were looking at, the commitment contractually is the output of what this equipment can do. So they'd say you can get so many units per hour or per minute or per seconds of this piece of equipment. And when this supplier would sell this piece of equipment, that's what they would commit to. What they realized was that when they were too conservative when they would commit to the throughput of their equipment. So if they said, hey, we can do something every 52 seconds or something, and then they would commission it, design it, they would adapt it to the customer's need, and then go there and say, oh, it was 45 seconds. So we could do better. But so they realized that being too conservative in sales, maybe they were losing sales opportunities because other people were bidding and were bidding more aggressive basically on the projects to buy that equipment. So the sales guys, hey, how could I get better? How can I commit contractually to get more sales? So in the same nature, this is an internal tool that was created for the sales team where they could submit customer parameters to the design. We had a full digital twin of the assembly, and from there we had a few simulations that were run to determine actually what the expected output of this machine was going to be. There was thermal stuff in there, there was structural stuff in there that allowed to figure out the amount of cooling time in the assembly for different components that were assembled, and from there they could actually contractually commit to it something much more aggressive that was reliable instead of not being reliable. So this was a process where the sales guy could submit this to their servers internally. 2 to 15 minutes later, dependent on the complexity of the assembly, they'd get that result back. So often even live in a discussion with the customer, they're having a workshop, they'd submit some ideas, they'd submit some variables, and they could say, yeah, we could do that in so many seconds. How would this work for you guys? And then they'd kind of iterate and change variables. So that was quite a powerful capability for them to develop. So I think the recurring theme, as you can see here, is kind of capturing knowledge, capturing rules, and finding a way to make them accessible to different people that have different skill sets. Not just engineers, salespeople, marketing people, anything that can help the business actually leverage the digital twin. So in summary, I've touched some examples today, but there's a lot more. We've done hundreds of different types of projects that are maybe more focused around simulation. Some are more focused around automation. Some are more just about a more reliable digital twin. We're talking about our, we have an algorithm group that does solver stuff. So if we need to develop new material models or develop different solver capabilities, we've done that as well. So here's just another quick brief view of stuff we've done for making non-CAD user tools. Someone who's never touched a CAD tool to do floor layouts or more complex design models. This is a data center that automatically does CFD models for a full complex data center, automated drafting or MDO, co-simulation. I think we'll talk a little bit later too, 1D, 3D co-simulation. These are just a little bit other ideas. And as you can see, there's different strategies. You can have small tools all the way up to full workflows or wizards. So it just depends on what makes sense for you, for your company, for your team. And from there, So again, we like to do projects. We have a nice team, a large team that's multidisciplinary. So Maya can definitely help you define that roadmap with you guys. There's different benefits, as you can see, with the right strategy, the right use case, you can actually derive a lot of substantial benefits from that. Later today, I'll talk to you about getting started. How do we actually define these projects? How do you get going from there? And there's an afternoon session today led by Charles. We'll actually talk a little bit more of the concrete nuts and bolts of and examples of how do you automate? How do you, what are the little tips and tricks and how do we do some of these things so that you guys have a better feel to concretely how do we do it and make sure that it's maintainable, sustainable, and stuff like that. All right? You guys have any questions for me? All right, well, I'll be available at the break if you guys have more questions.